Good morning, ladies and gentlemen, and welcome to the 2021 Solar Car Challenge Spring Webinar Series. We're excited to restart these series of programs because we're trying to help you be better prepared for the 2021 race at the Texas Motor Speedway. We've got great topics to present for you during these 8 sessions, including power management, how to get the most out of the power going into your car, steering and suspension, overall project management to get your team to the race, battery connections, relays in your electrical system, solar stop signs, stops and hazard signals, a typical day at a closed track, and significantly, an aerodynamic presentation by Mark Westlake with the famous St. Thomas Academy experimental vehicle team. So great things to help you be better prepared. And these are some of the people who are there to help prepare you. Standing is Chris Jones, who's our chief racing judge. Seated from left to right is William Shee, deputy race director. In the center, we have Jarrett Dunn, director of race operations. And to the right, partially obscured by my ugly picture, is Michael Foray, who is our director of communications. So these are the great people who will be predominantly running these workshops with guests from our sponsors at Siemens and our many solar car teams who are taking part with us in the spring semester. That's the best smile I've ever seen on any of y'all's face. So congratulations, gentlemen. I have 2 important dates to talk to you about. First off, if you are interested in being a part of the Solar Car Challenge, you need to file an intent to race form no later than January 31st. Now, this does not obligate you to race this summer, but it does put you on a mailing list so that you'll be able to receive all the notifications, event updates, be able to see everything new that's going on about the race. It just helps you be involved in the communications. Deadline for that is January 31st. You can find that link on the homepage of our website. Then, no later than April 30th, you need to file an official registration document. This is for teams who registered in the 2020 race that was postponed to 2021. If you did register in that race, well, then some of the details on your official registration probably are not going to be accurate, like names of the people on your team. So no later than April 30th, you need to file an official registration document with me, and you need to include in there a copy of your mechanical drawings. I'm going to offer a special cash prize for the best mechanical drawings in each one of the racing divisions as an incentive for you to put special effort in your drawings, which is part of our topic for today, the importance of mechanical drawings and schematics. So April 30th for your revised new 2021 official registration document. I'll be sending you copies of that, but it's available on the website. At the beginning of our fall webinar series, I talked to you about the importance of developing a timeline. Your timeline sets out goals for you. How do I get from here to here and have enough time to accomplish everything I need, from fundraising to building to testing and so on? But the problem has been pandemic has caused the schools to be locked down. Students have not been able to participate like they would like to, although some teams have moved their projects into parents' garages. Some teams are having now limited opportunities to get back to their work in the project. But revise your timeline, keep it relevant so that you can maintain a goal in here. There is nothing like having, whether or not it's in your classroom or in your shop or in a garage or something, a timeline that says, here is our plan. Here is what we want to do. It's huge. It's part of the process of goal setting and project management. So make revisions, get everybody involved in making those revisions so that everybody buys into these changes. That's hugely important. Have you ordered the construction materials you're going to need? This is always a real problem because here you are, had limited opportunity to work in the fall. Now you get ready to try to build your car. Have you placed your orders for the things that you need to work on it when you get to the shop? Which also means, do you have your fundraising efforts in high gear? One of the reasons why we wanted teams to prepare a video of their oral presentation that was to be presented to us back in July of 2020 was to use that video as a fundraising tool. You send that to a prospective sponsor, they see who you are, what your goals are, they see the students, they see your organization, and hopefully that'll help you raise some money. So as you think about ordering your goods, think about your fundraising. And you always have to ask yourself, are your mechanical drawings and schematics up to date? I've got to say that the board of directors and interns from the Solar Card Challenge are looking forward to seeing you in 2021. We wish you well. And I'd like to introduce Deputy Race Director William Shee, who's going to be talking to you about power management. Thank you very much.
Thanks, Doc. Well, I have the pleasure to talk to you about the exciting subject of power management. To me, when I first started thinking about building a solar car, I get excited about actually building a solar car. But as I went along more and more, the fun that I had was really thinking about how to strategize during the race. What is the best way of using the power that you get in the solar car that you built and running it in the race? And so I get to talk a little bit about that today. So when you think about power management, what is this all about? It's about the solar energy that you get coming into your solar car. How do you best use it? Now, every single team gets the same amount of solar energy from the sun, right? We're all on Earth. We go and we're all in the same local area, and so the sun provides the same amount of energy to all teams. Ultimately, though, is how do you convert that amount of energy into your solar car that's usable, and then from there, how do you really convert those into distance, into laps or miles? Because essentially, you don't get credit for the amount of power that you get in your solar car. You get credit for how many laps you drove or how many miles you accumulated on a race day. And so, how best to do that, how most efficiently to do that is really the game here. Now, when you think about your car design, your power that you use is dependent on aerodynamic drag, right? That a sleeker car like shown on the screen would have a better efficiency in terms of converting your power into your velocity or your speed. Of course, if you decrease your rolling friction, it would do the same thing. You would be more efficient in the use of your power. Lower weight also is a consideration. Electrical system resistance is another consideration in terms of if you have a bunch of cables that are a lot, are long and you get some type of current loss as you move the electricity across longer length cables. And so that might be a consideration too. Now, outside of your car, your driver's skill or style may also affect how much power that it takes to make your car go down the road. We know that you use a lot more power in an exponential way based off of acceleration. If you accelerate your car very quickly, you will use a lot more power to go the same distance than you would if you were to slowly accelerate. And so you have to consider all of those things. So how much power do you actually have to use? Well, if you think about a particular solar car, a classic solar car, for example, in a traditional, glass covered solar panel array, you'll get probably about 800 to 1,000 watts of power, maybe 1,200 watts of power. If you look at a particular race day, there's about 12 hours of usable sunlight. So if you look at the product of those, you should get about 9,600 watt hours of energy per day. Now, that's not really real, right? Because it assumes you have clear skies, you have a good sun, that you're always facing your solar panels towards the sun. And when you're driving your solar car around, you're not always going to be facing your solar panel towards the sun. So let's use those numbers for now and say, okay, you get 9,600 watt hours of energy per day. Well, we say that in our rules, you have 5,000 watt hours of battery capacity that you can put on your car and no more. But knowing how a discharge rate of lead acid batteries are, and how using the Picard's equation, the faster you discharge, the less energy, usable energy that you have are. So really, ultimately, the full battery pack usable energy is more closer to like 4,000 watt hours. And so you have to account for that. And we say that in terms of usable energy, it's about 4,000 watt hours. But then when you charge back up, you'll need 5,000 watt hours to charge it back up, because as you charge and as you go up to a full battery pack, it takes more energy to put that into your batteries. So ultimately, that might be a starting basis for how much power that you have. Now, let's talk about strategy considerations. Dead batteries are dead weight. One of the heaviest components of your car are your batteries, right? And if you don't have capacity to store that energy, then ultimately, you're just carrying that weight. And we said weight is a consideration for how much energy that you use running a solar car. And so if you have a full battery pack at the beginning of the race, and then you start draining it down and can never charge back up again, well, you're essentially just carrying dead weight. We say that especially in lead acid batteries, your 48 volt battery it's not a 0 to 48 volt range, right? It's, in a particular lead acid 12 volt lead acid battery, you have about 10.5 volts wait before it's really dead. And so a 48 volt battery pack is dead at 42. So that's your range of voltage that you have to play with. And so when you start monitoring that data, you'll want to keep an eye on that. Now, looking at the numbers from before, and if you have a full battery pack of 5 kilowatt hours, and you get about 1 kilowatt coming in on your solar array, it will take at least 5 hours of full sun to completely recharge a dead battery pack, right? And that excludes hills and clouds and trees and wind, the fact that you're not aiming your solar panel towards the sun at all times. And it accounts for, if you're displaying your car, you've got people, touching your solar array and leaving residue on there. We've had lots of fun. We love going out on these road races and meeting with the community, but there are folks that love to see these cool things and start putting their sticky little fingers on the panels and leaving residue. That really affects your efficiency, just like any other shade would. And so, the optimal calculation would be, okay, you get 1,000 watts coming in, you got a 5 kilowatt hour battery, it'll take 5 hours to charge, everything's good. But really, ultimately, the only way to know how much energy your car will take in from the array and how much it will take to use in order to drive and convert your energy into distance is to test it. And that's one of the key things that we definitely did when I was racing, is to take our car out, test it a lot, start recording down. Well, at a particular speed, what is my current draw at cruising speed, right? Not in terms of the acceleration to get to that speed. And you'll notice that is not linear. And we'll talk a little bit more about that. I have some real data that I have for you coming up to look at. Now, before we start thinking about that, as a team, you have a set of strategic decisions to make. So even without looking at the numbers of inputs or outputs of your car, you have to figure out what is my high-level strategy for running a particular race. You have lots of options, and some options that I'm showing on the screen are just some of them. There are lots of other options. But let me walk you through each one of them as examples. So one, do you empty your solar car battery pack each day and recharge it as much as possible during the off hours? So what that strategy is to say, I've got a 5 kilowatt hour battery. I am going to spend the entire day, the first day, for example, draining a full battery pack to 0. And then at the end of the day and at the beginning of the next day, because the day ends at about 5 o'clock of racing, and then there's some time to charge your battery pack at the end of the day, and then we start racing at 9 the next day, so there's some time to charge your car coming out in the morning. And so you could strategize and say, I'm going to completely kill the battery pack at the end of the day, and then I'm going to charge back up and have some amount of energy at the beginning of the next day, right? That is a possible strategy. And the benefit of that is to say, you are never carrying any dead weight in terms of you're using up all your power. However, at the beginning of the next day, you don't get a full battery pack to use. And so ultimately what that looks like is you're going to go really fast on the first day. And then the second, third, and fourth day, you're going to go slower because you have less energy, right? You have 5 kilowatt hours plus your solar energy to use on the first day. And then the second, third, and fourth day, you simply have solar energy. Another strategy that you could consider is, okay, let me flip it around the other way. Do I end the day with it drained down to the point in which I know, let's say, and the end of the day and the beginning of the day, I can recover about 1,000 kilowatt hours of or 1,000 watt hours of energy. Well, I'm going to make sure that I only run the battery down 1,000 watt hours of battery. And then so I know that at the beginning of each racing period, I have a full amount of energy every time. And so the benefit to that is, hey, you've got your entire full battery pack the entire racing, every racing session. So, you've got that buffer to account for anything that might come up, be it, a shade, clouds, whatever, what have you. But the downside to that is, well, you're likely going to go slower on each day because you're only using the energy provided by the sun. You're not actually taking advantage of some of the capacity that you're freely given because you can have a full battery pack at the beginning of the race. So there are pluses and minuses there. Okay, so one other possible strategy would be, okay, let me meet in the middle. I've got a 4-day race. I'm going to take a quarter of the battery pack down each time so that by the end of the entire race, I'm completely drained, right? And so that's certainly something that you can say, okay, well, I'm going to drain down, let's say 1250 watt hours plus whatever energy I would expect to get at the end of the day and the beginning of the day. So at the beginning of the second day, I'll have 75% of my battery capacity. At the beginning of the third day, I'll have 50% of capacity and down the road there. And so that is a benefit to be able to use some of the battery capacity that you're given at the beginning of the race, but yet still making sure that you can account for um, your solar energy that you get further down during the race racing period. Now, the downside to that is going to be, well, you're you don't know what the future looks like, right? So you don't know how much energy you would have on the subsequent day. You may ride slower on other days because you might not get as much energy, or you might get more based off of the sun or the clouds or the weather. You may have variabilities in terms of the speed that you can run on any particular day. The other thing to consider is any of these particular strategy, you're going to have to look at how your car performs, right? There might be some optimal speed that converts your energy to distance most efficiently. And any one of these strategies may not account for that. And so you may say, well, I can run 15 miles per hour running at a particular strategy, let's say the last strategy option, but yet I'm most efficient at 20 miles per hour. And so maybe I actually need to run my battery pack down further to, let's say, a third of the battery pack, and account for that in my future planning. And so it's really, ultimately, there is no right answer, right? It's really your team needs to go through these considerations and decide, well, how do I want to run the race? The other consideration you need to look at is how you actually calculate for the decision. Do you make decisions based off of net draw or motor draw? And net draw is simply saying, I can direct the driver to say, pull 15 amps out of the battery as the speed, right? And so whatever your solar energy that you get from your array, plus your 15 amps, that's how fast the driver drives. And that's nice and easy for the strategy team to be able to say, oh yes, I know the rate of discharge and the rate of charge. It's very easy to calculate. But based again on clouds and shade cover, you may have a lot of varying speed based off of that, and that may or may not be most efficient use of your energy. But if you decide, I'm just going to tell the driver, go 25 amps, regardless of how the solar array is putting in, then your power management strategy needs to accommodate for that and say, okay, I need to predict how much energy is going to come up in the future and go from there. So, again, no right answers, but some considerations for you. And this is what makes things fun for me. Just being able to do this type of thinking and strategy rather than just driving the car. So let's say you chose a particular strategy. How do we convert that into tactical decisions? So if you look at a particular strategy, let's say we decided to empty the battery pack each day. That's our strategy. And we have a 100 amp hour battery pack. How fast should the driver drive? So in a normal interactive workshop, I would say, hey, I would just pause here for comments. But if you're in and watching this, maybe you can go ahead and type in the chat window, hey, I think I know how to do it at this speed or that speed. But ultimately, that's really a trick question. You don't drive based on speed. If you have the ability to have characterized all of that and know that at 20 miles per hour you can certainly drive at 15 amps or things like that, well, okay, you can tell the driver to drive that speed. But ultimately, in terms of power management and direction to the driver, you really ought to tell the driver, hey, expend this amount of energy, expend 15 amps as you drive. So that's sort of the first thing. Now let's go, okay, we know that. Now we're going to do current draw, right? So I've got 100 amp hours of battery pack. I've got 6 hours of racing if I'm in the classic division. So the driver should be driving, and taking the net draw of 16.7 amps, right? Yes, to some degree, but you do have to exclude the idea of Puchert's equation, the idea that if you discharge your battery faster, you will get less usable energy, and so you can't really draw 16.7 amps. Over the course of 6 hours. Because if you think about a battery capacity, those battery capacities typically calculated at a 20-hour discharge rate. And so if you discharge at 6 hours, you will have a lot less usable energy there. So next consideration. If you have a car in the classic division, we actually split up the racing into 2 racing periods, right? And so you have a 9 to 12 and 2 to 5 period. So while we have 6 hours of racing and you have 100 amp hour battery, you can expend 16.7 amps. You actually get some charge back during those 2 hours of charging. And so you got to account for that. So if you assume a 1 kilowatt panel over a 48 volt system, you're probably going to get about 20 amps because it's power is current times voltage. And so over the course of 2 hours, you should be able to recover 40 amp hours. And so that's additional energy that you need to account for. So if you had gone and expended 16.7 amps over the 6 hours, you would expend 100 amp hours of capacity, but you get back 40 amp hours. So ultimately, if you didn't account for that, you would be running the first 3 hours at 16.7 and need to actually run at 30 amps on the second half of the race in order to fully expend your battery. You don't really want to be in that range of I'm going to run slow at 16.7 amps in the first session and 30 amps in the second session as a plan, right? You really want to try to even it out because it's going to give you better efficient conversion of your power to your running. So you might ask, well, how do I account for that? And so what you can do, of course, is you can just take your 100 amp hour capacity, you have your 40 amp hours you're going to collect during the charging session. So you have a total 140 amp hours over the course of 6 hours. You should be expending 23.3 amps over the course of the 6 hours. And so that's really how you might do some of the calculations and how you convert a high level strategy into your tactical decisions. Now, of course, as you consider that in your pit slot on any particular day, there would be all sorts of other variables to consider, including how much energy that you get from the sun, including how the batteries are performing. There might be some considerations for other drivers on the racetrack and whether or not you need to reserve some energy for passing or for driver changes and things like that. So there's all sorts of other tactics to deal with, but at least in terms of calculation, that is a way to get you to some overall target you can tell the driver to drive. So if you start looking at all this stuff, though, you go, wow, that's a lot of data. How do I collect that data? And so one of the ways you can simply do it is via a voltmeter and ammeter. You can actually just attach something on, and you can have the driver go and report that via radio and take regular measurements and write it down. That's the very simplest way of doing that. Of course, there are other better systems out there. What you see on the screen is a Batman measuring system that's made by Bruce Sherry Design that gives you all that information, including a amp hour counter, right? It tells you the state of charge of the battery because it does all that sampling and calculation for you. So that's certainly an easy way of getting that data. What we have used in my previous solar car team is what's called a Link 10, or the old name was an e-meter. It's this little round meter that shows you, voltage, current, battery capacity, sort of the same thing as a Batman. And if you notice both on the Batman picture and if you look at your Link 10, there are instrumentation outputs that's a serial port output like an RS-232 as you see on the screen that you can use to siphon off the information and put it into a telemetry system. If you can design a telemetry system that can collect all this data for you, you're going to get the most accurate data. Having a driver have to radio back in regularly and say, hey, it's got, I'm at this volts and this amps now. You can't account for all the varying changes that the way you drive the car. And so something to consider there. But if you're starting out and you don't have that, just have the driver report it regularly and write it down and do your calculations there. We've done it both ways. It's just you get better fidelity if you had a telemetry system to report it. Okay, so you go, okay, I can collect the data. Well, what data is important? It's really based off of your strategy, right? What do you need in order to execute your strategy? So typical, I would say the minimum that you would want is battery voltage, and battery voltage that's measured under load. If you have no load on your car, if you've disconnected your motor and controller from your car, your battery voltage tends to float up because there's not really a way to measure the more accurate voltage. So you want to get the voltage as you're running the car. You'll want, of course, the motor current draw because that's the rate that you're taking the energy out of your batteries. You want your array current because that's the rate that you're putting the energy back in, and you need those numbers to be able to calculate what your net draw is. Am I putting more energy into the battery pack, or am I taking energy out of the battery pack? And then I would say optionally, and I only optionally because you have the information in front of you, but if you have an amp hour or watt hour counter that shows the state of charge, it gives you more information in terms of you don't have to calculate for it, right? It just tells you, hey, my battery is at this level now. So that's nice to have. So in previous teams, we have collected some information, and I'm going to show you information from a race that I participated in 2017. This is the Walnut Solar Car team. Collected this information via an automated telemetry system. I am freely sharing this information with you, primarily because that team doesn't exist anymore, so they don't mind that I'm sharing their information. But this particular chart shows you the charging characteristics of an electric solar division car on July 21st, 2017. I will say that would love to get your thoughts as you look at this chart via the chat or via the question and answer, and tell me what is interesting about this data. I'll walk you through some of it as we go along as well. But if you see some interesting things, bring it out. One of the things I need to show you is the particular axes, right? So the main battery voltage is in orange, the main battery current is in blue, and the power, or the product of those two things, is in watts, right? And so when you look at main battery current, it's really the current that's being put into the batteries from the array. Another thing you need to know is that in an electric solar power division, your charging happens in a separate charging station. And so you will not see any decreases in the battery capacity because this is only the charging side. You'll also notice that the power and the voltage goes to 0 at specific places in the graph on the x-axis. And that's because we actually do battery swaps in this division. And so we have to disconnect the battery at that time and put it in the solar car and then put a new battery pack onto the charging station. So that's why it goes to 0. If you start looking at this data, you'll see that in the morning, the power is about 1,000 watts that's coming in, other than at the end of the morning session. And we'll talk a little bit more about why that's the case there. In the afternoon, though, it's a lot more erratic, and we can discuss a bit what that means as well. There are some dips in terms of the collection of data. That's really an artifact of our telemetry system and the sampling. And so don't worry too much about that. Just move out the graph. And then finally, you'll see the width of each section between the zeros. And that will show you how long we ran that battery pack for. So for example, the first battery pack ran for about 50 minutes, right? 9:41 to 10:35 is how long we ran the first one. And then it successively gets less and less, right? The second battery pack got something more like 40 minutes. The third one got something about 30 minutes. And that's really a factor of the expenditure side, the discharge side, where we were running the batteries down very quickly on the racetrack, and so we needed to do a swap earlier. So some of the other comments that we saw is like the voltage in the pack goes up as we use it. In this particular drawing, this is just charging characteristics. And so this doesn't show the discharge that's sitting in the solar car. And so you will see the voltage always go up because you're putting more energy in from the solar array. There are dips in the voltage on the afternoon, and that's ultimately just a data collection artifact. It's not real per se. And so something to consider there in terms of looking at your raw data. Okay, let's analyze this a little bit more. So you can see, as I shared, the power stays fairly constant through the racing period, 1,000 watts. That's how much the energy we get from the solar array. And the benefit of the electric solar division in a charging station is you can actually tilt your panel towards the sun at all times. And so that's why you get a very constant collection of energy. In a solar car where the solar panels are on the car, you're not going to get that level of consistency there. You'll notice that the power input drops near the end of the charging period. And that's ultimately that we decided at the end of the racing period to not come in for another battery change, right? And so we decided, you can see the width of each of those are successively shorter because we were trying to drain it down. But then we go, well, our strategy was we didn't want to take another time penalty because it takes time to swap out the batteries. We didn't want to take another time penalty to go and swap that battery. So we decided to slow down in order to preserve that battery pack that's being run in the solar car and just let this sit on a charging station. Well, that means that that particular battery is going to be at its near full by that time because we've filled it up. It's been charging for so long, and so we can actually pack in less energy into the pack because as the battery gets full, you would need to drive more energy into those batteries. And then the battery voltage remains stable even though the current changes, primarily because the power tracker will help adjust for that and make sure that the output voltage is a consistent level, just higher than your battery under load, in order to put as much current into the batteries. A question that was asked is, did our batteries fill up after noon? And yes. So if you look at that, the charging characteristics, we're basically already filling up at around noon, right? And so we're just sort of like putting the last bits of that in, and which also means that when we ran for our charging period on the during our noon to 2 period, we're actually charging the other battery pack, right? Rather than charge the first battery pack. So some sort of interesting data for you, and this is the type of data that you need to characterize in your solar car and your charging system in order to be able to make certain decisions, right? Without this data, I don't know that, for example, I can actually charge the battery in about an hour's worth of time. I wouldn't have known that. Now let's take a look at the discharge side. What's interesting about this data? And I'll walk you through some of that. The y-axis is the speed, and the x-axis in negative is the current draw. And so we tend to say that current draw is negative when we pull current out of the batteries, and then current draw is positive when we put it into the batteries. That's just the way we programmed that. And so I'll let you take a minute or so to take a look at this graph and say, what is interesting about this particular piece of data. One of the things to look at is there's a wide range of data points right here. I can be going 25 miles per hour, drawing 0 amps, which is the far right, drawing 10 amps, 12 amps, drawing 88 amps on the far left. And then I've got this mass of data that says, for the most part, I'm drawing out 25 to 45 amps going 25 miles per hour, right? You also look and say, well, there's this big sort of like square-ish glob here, right? Where I'm taking the same amount of current draw at 20 miles per hour and at 25 miles per hour. Why is that? So certain interesting things to look at here. Okay, let's take a look. First off, current draw is not directly correlated to speed. It's correlated with acceleration, right? So when you think about that, you're going to spend some amount of energy getting your car up to speed, and that's going to use more power. And then when you get up to speed, you might be at a cruising speed where there's some type of maintenance amount of power that you have. And so that's really what that big glob is the characteristics of cruising. Now, you might see a lot of zeros too. And that's ultimately, if you have some downhill sections, even on the track, going around the track, you might have some uphill and some downhill. And as if I ride bikes a lot, if you're riding your bike down the hill, you don't really have to pedal to keep your speed, right? The momentum will just take you down that path. So likewise, in the solar car, there may be times in the day where you're going downhill and expending zero. So that's sort of some of the interesting characteristics of this graph. Now, these outliers, you have to start characterizing these outliers. Is that outlier because you just have a bad driver that decided to floor it as he accelerated? Or is it that there's some characteristic of acceleration for all drivers that make that difficult, right? That say, I've got some amount of drag that's causing a bunch of stuff that's going to slow down my acceleration, require more power to get up to speed. That might be another consideration. So you'll need to test for that. But this type of information, and especially if you have it per driver, could help you characterize how well a driver is doing, how well your car is doing. So, if you look at that, again, a lot of data points. Each dot is really a data point that we collected that said, I'm driving at this speed, and I drew that amount of energy. So how do you get the right data? Ultimately, test. It's all about testing. If you don't test before you come to the race and collect all that information, you won't know anything when you get to the race. And so you won't be able to make these type of decisions. Even if you had a strategy, how would you know how fast to run the car? You don't have that piece of data. So in my solar car teams, we would build the car, have it ready by March or April, and then just continue to run and collect this data. We happen to work in an industrial area in one of my teams where there's a road that's out in front that is not used on the weekends, right? It's very busy on the weekdays. It's not used on the weekends because this is an industrial area and businesses are closed. And so we were able to run, and there's a slight uphill and a slight downhill going back the other direction. And so we were able to run our solar car up and down that road. It's about a mile long, and be able to run it at different speeds with different drivers and collect all that data and determine, well, we know that if we run at 30 miles per hour at cruising speed, we got about 20 amps out of the batteries, or so on. And so you do that, and you do that by collecting that data and then changing a particular parameter. On a particular run, you might say, go 10 miles per hour. Next run, go 15 miles per hour, go 20 miles per hour, and so on. And do it both directions, and do it with different gearing ratios. So that might be important as well. Ultimately, you want to get to the point in which you hold simulated race days. Actually go and wake up at a particular time, put your car out to charge, discharge, run the entire car throughout the day, and you get some more realistic data that way. So how do you make decisions? You'll be in the pit slot at the track, and you'll be sitting there watching the racetrack, and your car is out on track. It's really the team that's back here that's going to be able to do all the calculations and determine, what is the driver supposed to expend the current. So getting that to the right people. The driver shouldn't be making decisions other than driving. The driver they don't have all the data in front of them. So the driver shouldn't be determining, hey, I feel like going 25 miles per hour right now. How do you know that's the speed? How do you know the state of charge of your batteries? Even if you're radioing it in, you may not know the rate of change. So the driver, you've got a lot of things to worry about, especially with cars around you. You've probably got a spotter that's helping you, make sure you're avoiding obstacles. You should just drive. It's really the pit crew and really the strategy team that should be telling the driver, maybe drive at 15 amps or speed up or slow down. They should make the decisions. And one of the most important things is only one person should be communicating with the driver. You don't want a team of strategy people that says, hey, go 15. Oh, no, go 20. Go 25. No, the driver's going to get confused. What happens should be that the pit crew goes and talks amongst themselves, figure out, okay, what is the current draw we want, and then radio the driver, driver, we want you to drive 15 amps right now. Nice and clear. And then telemetry systems, of course, can be used. You can design a telemetry system to not only input the data, collect the data for you, but you can also do some data crunching and actually calculate for an optimal output. And we did that in our telemetry systems where we estimated the amount of current draw, or the amount of power coming in from the array throughout the day. And we can say, okay, if we want to match our strategy, well, it will actually spit out, this is the current draw the driver should be driving at. So certainly can program some things to help you get there. Now, choosing the correct gears. So in terms of your car design, and as you do your car design, your gearing ratio is going to affect how much power you're going to use for a particular speed. And because each motor generally has a range of RPM that's most efficient, you're going to gear that down to the speed that you want to run. First-year teams are probably going to be very excited to say, I want to go really fast. And they'll gear their car for a much higher speed than you would actually drive in the race. And that, what the effect of that is, you're going to actually run in the motor's inefficient RPM range because you can't expend enough power to get there. So if you look back at our data and our results from our solar car webpage, you'll know that the winning solar cars average somewhere between 20 and 25 miles per hour. So don't gear your car for 50 miles per hour. You don't need to get there, right? And of course, you'll need to maintain your drive system to get the most efficient use of that. But one of the pictures here, you can see a 15-2 front, 72 rear, and that max speed is about 36 miles per hour. That might be where you want to be. In terms of my team, we had a 13:108 ratio, even larger. So it would be a lower maximum speed. Okay, so some other considerations that you want to do once you start figuring out a lot of these high-level strategy and getting the data to execute that, it's, how does weather affect charging? You should go out and test and say, if I had a cloudy day, or if I had a rainy day even, what effect does that have on charging? Not that we would go and operate when it's raining. Based off of different angles of the sun. If you've got solar panels on your solar car, well, if the sun is at a particular angle, how much energy do you lose based off of that? Your array shapes is another issue. Route topology or track layout. As we run around the track, based off of the track orientation, the sun would be in a particular spot at different times of the day. That might affect your power usage. So there are other considerations that you want to research if you have the time to do so to optimize your power management strategy. And of course, there are other considerations that I'll let you think about as well on your own. There's lots of different things to think about. But closing up this section of the presentation, really ultimately in terms of power management, you need to determine what is my high-level strategy for how to best use my collected solar energy. Am I going to drain the batteries every day and charge it back up at the end of the day? Am I going to do, drain it at the very end? And once you have that strategy, how do you execute it? You test to collect that data so that you can make your decisions, analyze that test data for trends so that you know this is how the car operates at this particular speed, at that particular speed. And then train your strategy team during a simulated race day to look at your real-time data and make decisions. There's going to be all sorts of data that's going to come in, and you need to be able to quickly look at that data, look at what's important versus discard what's not important, and then make your tactical decision. And then that'll allow you to, when you get to the race, better execute your plan. So I just thank you for the opportunity to talk to you about power management. If you have any questions about this topic or any other topics here, certainly send a question to me at she@solarcarchallenge.org or to Dr. Marks at solarcarchallenge.org. And so at this, yes.
Before you pass this along to Jarrett, I want to remind everybody, this is why they call solar car racing the brain sport. Your presentation shows that this is not a pedal to the metal type of project. It's where you go through and you use the kind of information that you can gather through testing to help run your car. I'm very proud of your presentation. Good job.
Thanks. At this point, I'd like to pass the baton over to Jarrett Dunn, our race operations director, and he's going to talk about the importance of properly prepared mechanical drawings and electrical schematics. Jarrett?
Thank you, William. We were talking about the importance of properly prepared mechanical and drawings and electrical schematics. So these are really fundamental to what we do, is designing and building construction of things. So what we're going to cover today on our agenda: why do we need properly prepared drawings and schematics, cover the rules, benefits, go over some best practices that we've seen over the many years we've been doing this, and we go over some sample drawings that we've received. Okay, well, the number one reason you need good schematics and drawings is our rules require them. Rule 3.6.1 requires that you submit mechanical drawings, and the penalty for not doing it is you'll be disqualified. So that's a fairly important reason to include them. Rule 3.6.2 tells you that you have to submit electrical schematics. Okay, also, as you're going along, different teams are going to have different levels of talent and different schools have different capabilities. At some point in your project, it's very likely that you're going to have something that you can't make or something that you think someone else can make better. And it might be machining a hub, sending your solar array out to Suncat or Allen to have them tabbed in, or it might be welding some kind of difficult process or part. Rule 3.8 says that parts may be fabricated by specialty shops. So you can send something out to be welded or machined, but the students have to specify what the specialty shop is to do through drawings or specification sheets prepared by the students. And this is one of those things that's really important, that you prepare good drawings. If you're going to send something out to a professional, well, they're professionals. They're really good at what they do generally. That's why you're using them. So the better the drawings you give them, the better that they can help you. So when you send a drawing to a professional, they're going to look at it, and very often they're going to make suggestions on ways that you can do it better, cheaper, faster. And so the more information and the easier it is for them to understand, the more likely it is that they're going to provide good feedback to you and help you make a good product. Okay, and so that's the rules. And if most of you are like me, that's telling you because the rules say so. It's not a very satisfying answer to why you need good drawings. I mean, it's important, but do we do this just to make it for our own amusement, to make work for you? No, really. Having good drawings is really important to you. having good solar car drawings is important to having a good solar car. Notice I didn't just say a solar car. Quality teams require quality planning. And there are very few things in life that you're going to excel at without a good plan, and solar car racing is no different. Then there are lots of kind of plans in solar car racing, including your schedule, your budget, but probably the most important for actually constructing your car is your drawings. First off, drawings help you identify issues before they become problems. It's a lot easier to fix your solar car when you're in your home shop with your own tools, your own suppliers, and most importantly, your time, than to have a problem identified at the Texas Motor Speedway and be struggling to fix it in the garage with a crunch time as you're stressed and everyone's going. And yeah, it's much easier if you can identify those problems easier. Also, good plans help you select the right amount of material so that you have the parts and things needed available. There's nothing more frustrating than fabricating your car, getting down to the last minute and realizing that you're one stick short of the metal that you need, or you have a 6-pin connector when you actually needed an 8-pin connector. If you have the good drawings and a good plan, you'll know about these things ahead of time so that you can plan accordingly and have the right materials on hand. Second, the schematics are a record of what you do. And that's very important when you come to troubleshooting your car. So one of the stories that I have that I will remember for as long as I'm doing solar car racing is working with the Colorado team many years ago. And while you couldn't do this now, the Colorado team had a hand-controlled throttle. And during the course of the race, they decided that this really was not working out for them, and they were going to convert to a much more conventional style of throttle to do their foot. Well, their potentiometer was tied into a big wiring harness, and they started taking things apart, and they got to a point where they had 12 wires, and they were different colors, they were different shapes, but they didn't know what any of these wires went to. So they spent an entire day trying to find where each one of these wires went to find the important parts to connect their throttle back, their enable switch back, and what really stumped them for the longest time was their safety switch. And they lost an entire day of racing because they didn't have a good diagram. Whereas if they'd had a good electrical schematic, they would have known that the red wire was the power and the purple wire was the safety switch and the green wire was the potentiometer and all that. So just an example.
Hey, Jared.
And also in troubleshooting, it's very often that I've noticed that there's 1 or 2 students who are really good with electrical work, and they do a lot of the car. And sometimes those students, for some reason or other, they graduate. Well, I guess that's probably a good thing that they graduate. They get sick, they take an internship, but they don't show up at the race. So, and I tell this story pretty much every year. So if you've been with us at one of our conferences, you'll have heard it before because it involves one of our staff members, and I love watching him turn red when I tell the story. But we had a team who was having a problem with their solar car. And like many teams, they were not unique by any extent. The young man who designed the electrical system wasn't at the race. So it left other individuals to try to troubleshoot the work. And their batteries were not charging. So went to start troubleshooting the problem. And anytime you're troubleshooting a problem, you want to start at one point and logically work through it. Well, they didn't have any electrical diagrams, so we didn't know really where to start. So, okay, well, we started the solar array. Is power coming in? Okay. Yep, we're getting power from the solar array. Okay, well, what's next? Well, if you'd had a good wiring diagram, you could have gone and looked. They didn't. So, okay, we'll trace the wire. The next thing's the power tracker. Okay, is power coming into the power tracker? Yep. Is it coming out? And so forth and so on until we worked all the way down through their problems. And eventually we found that the wire leading to the battery wasn't connected. But having a good record of what they had done would have significantly saved them amount of time as they troubleshooted to identify where they needed to look. So those are the real reasons why having good diagrams can help you. Also, it helps us help you. As part of your race package, it's just the requirements from the Rule 3.6 that you submit these drawings to us. We have a very capable team, including William and Chris, who are on with us today, who go through all the drawings that you submit, and we look for problems, or we look for common issues that we see. And as I said earlier, we're not going to catch everything, and sometimes we don't have all the information, but we're very good, and we make an honest effort to find it. And it's much easier to fix those things when you have a month in your own shop than trying to catch them at the last minute at the speedway. Okay, and so when we do this review, some of the common issues we see are insufficient roll cage clearance. And this is probably the most common issue that pops up time and time again. You have to have your 15 centimeters of clearance around your driver in all directions. We also see very often that the roll cage does not encompass the driver, or we don't know if the roll cage encompasses the driver, and we'll find that out at the track. Very often crush zones are not labeled, so we don't know. It's very hard to say if the crush zone is sufficient if we don't know what the crush zone is. Or crush zones might not be missing, or might be missing altogether. On electrical diagrams, very often important components are missing. The fuses, having all 4 of the disconnect switches. Also very common for the fuse not to be the first thing in series as is required. And also very common to be missing the low voltage alarm.
Hey, Jared, can I jump in for just a second?
Please.
I thank you, William. I didn't realize my microphone volume was so low. You'd given a bunch of stories, and you covered pretty good all the pitfalls on the electrical side that happen, both while you're building up the car and once you get to the event. Your electrical schematics totally dictate how well you're going to be able to troubleshoot a problem, because if you don't have a good roadmap there, you're literally digging through sometimes a spaghetti mess of wires, having to have somebody on one side and somebody on the other side just probing things or disconnecting. Whereas if you'd actually documented it well, you can troubleshoot it on paper before you ever go to the car. But one of the things that I wanted to stress, having done it both ways, way back before most people were around, back in 97 through 99, the tools that we had available to us for doing CAD drawings were quite a bit different then, especially for 3D modeling. So we had parts of the car where we had done it really ad hoc, where it's like, I'm going to just go ahead and try and build the rear wheel assembly in place. I've got a rough idea. I sketched this out on a whiteboard. It'll be fine. I'll get in there and do this. You do a bunch of welding. You cut a bunch of, for us at that time, it was steel. You put something in there, and then you discover that you don't have clearances, or you discover some other mechanical interference, or you discover that although you welded this motorcycle rear swing arm in place, you actually have no way of taking the tire off now because everything's been locked in the frame of your car. Your drawings are your design. This is how you check that stuff ahead of time so that you don't do what we did back in the early days of this sport, where we kind of had no choice but to brute force it, get caught, and then spend 2 or 3 days in our shop undoing all the work that we did with something that we easily could have seen if we had sketched this up. So I just wanted to point that out, that, you know, we've had some really good successes, and most of those successes came when we actually did our engineering ahead of time with the drawing, with the tools that we had, versus I think we can just tackle this in place. It'll be fine. So we'll sketch it up later so that we meet the rules. But that is not the tact I would recommend taking. And sorry, I didn't want to derail your point. I was trying to slip it in earlier. I just couldn't get loud enough.
No worries, I appreciate it. Yeah, Chris is absolutely right. There's nothing more frustrating than when you realize that you've done something stupid and you now have to sort it out in real time, which is, I've been guilty of that many times myself. So some of the best practices we've identified is to label your drawings. We see a lot of drawings without dimensions. 2 millimeters, 2 centimeters, and 2 kilometers are all very different things. So without the scale, without the information, it's very difficult to know what you're looking at. Just one of those humorous stories. I have a client that I work with that's in the textile industry. And I have no idea if it's industry standard or just a quirk of the German company that I work with. But for some reason, all their equipment and all their designs are done in decimeters. Decimeters are not exactly a standard unit, but most people look at the drawings, and the drawings are labeled, but they're not a standard form. And so there's a little block that we'll actually show you later where most people put the units, and that's not where they are. They're in the comments for some reason. And so it's very obvious that if their units are not in millimeters, because the part would be microscopic. But more than once, they've had a part to show up that's 10 times larger than they were expected because the person making the part assumed that it was in meters. So those little details are important, and labeling is very valuable to you. One other one is color is your friend. You can use color in your mechanical designs to show your crush zones, your roll cage, what's the structure of your car. On the electrical, you can show the different colors of wire that you have. Wire comes in many colors and stripes, and it's amazing. And definitely do not limit yourself to wire your car in black wire. There's nothing worse than troubleshooting a mess of black wires.
I will second that. Pick more than one color. You have more than one thing on your car.
Yes, and make all your 12-volt wires one color, all your high voltage color wires another color. Make all your signal wires for your potentiometers for your throttles a different color, and label them on your drawings and make them in color on your drawings. And it's wonderful. Another one that's useful is to actually use a model of your driver. We see lots of solar cars, and they're beautiful cages, beautiful designs, but it's really very hard to see how they're going to fit, how they're going to work together without a model of your driver. Okay, so these are some of the models of our driver. On the left is a very accurate model. That is Bob Jr. He's 5'8", 120 pounds, has a 28-inch waist and 38-inch shoulders. So he's very accurate. This is a little bit more complex CAD work. It's made with a program called MakeHuman, which is an open source free program. And it involves Blender, which is another open source program to export them into a format that you can use in a CAD program. But it's very doable, very accurate, and you can get a lot of information. The guy on the right is called Blocky. He's 6'1", 240 pounds, has a 38-inch waist and a 42-inch shoulder width, which turns out to be exactly me, because that's the model that I use when I'm designing workstations and things for me to see how I fit next to them. And that's a very simple model that took about 5 minutes to do in CAD. And I'm sure our friends from Siemens who are with us today will be glad to help teams create similar models for their drivers. And so this is a nice example of the roll bar and crush zones of a solar car. If we got these designs, I would be very excited because this is an excellent design. One thing that immediately comes to note is it has no front or rear crush zones, but we won't dwell on that for the moment. But it has the roll cage that's required. It has the front support to keep it from folding forward and backwards. We've got crush zones for the side and going up the side of the body. So I would say everything on this looks really good. but we noticed that there are no dimensions on it, so it's very hard to say. And even if there were dimensions, we'll say the bottom was 24 inches. It's very hard to figure out what that means.
Jarrett, before you, can I respond to a question that Ricky asked?
Please, I didn't see it.
Yeah, one of the rules said that we have to encompass the head and the upper body, and we have to have front and rear crush zones. And you're about to demonstrate this right here, where you can see where you've got the model in there. It doesn't mean that you totally have to wrap the driver so there's zero way for them to egress the car, things like that. But Ricky, you can kind of see from Jarrett's example how there's a crush zone, especially in the middle view, that comes up and it covers the driver's head and upper body, versus something that would have just stopped at waist level. Like if you go through and you look at some of the classic cars that we've had in the past, where we'll see something down low, but the whole upper body of the driver is exposed. And that's what that rule is trying to get away from. The windshield doesn't count as a crush zone. What we mean is that you have to have something in the front of the car, something in the rear of the car, and generally something surrounding your driver, like Jarrett's illustrating here. I don't know if that completely answers your question or not, but we can always talk more over email or over the phone, or please feel free to add something else to the chat if that didn't quite answer what you were asking about.
Okay, yeah, and please feel free to chime in on chat or questions anytime. I didn't have that window open, but I do now, so we'll see them. And I'm getting forceful backup from William and Chris, so that's outstanding. So, well, now that we've thrown our driver into our example, you'll notice that our driver is quite tight. I don't think that there's any chance that he's going to meet the minimum requirement of the, I think I gave the wrong number. I gave the crush zone distance instead of the distance between the structural members earlier, but he's not going to meet any of the distance because he's quite wedged in there. So this is where these models can be very helpful. Even my simple model of Blocky would have been able to tell you very quickly that you're going to need to do something else. And identifying that now on paper, CAD is electrons are essentially free, and CAD software can be kind of expensive, but our friends at Siemens are going to help you with that part. And it takes time to build models, but I can assure you it would take less time and certainly less money to have identified that your driver does not fit into your car here in the computer than having built it, sat in the driver's seat, and realized that you don't fit.
I would also say, from my perspective as chief judge, that it is never fun for me when we have a driver in a car that doesn't fit, and I have to tell them that, maybe this is their senior year, that they're not going to be able to drive the car because they don't meet the clearances. It's kind of like Jarrett's illustrating in here. The driver's just too big, and a little bit more work early on could have given you a chance to make the car better fit all your drivers.
Okay, so we'll move on to some of the drawings that we've actually seen. So these are the next couple of drawings are samples that we've taken from actual submissions. We'll leave names out of it, and these are neither good nor bad. They're just samples that I picked to kind of illustrate how we go through and identify some of the issues and pitfalls that we see coming through. And there is no right way or wrong way, so I've got a couple different styles of models, but how you present the information is entirely up to you. And I learned a long time ago, it's not great to say this is the way to do it, because then everyone will do it, and there are that way. And there are lots of good ways to present the information. So this model is one of our teams. It was a very well done CAD model, but you'll notice that there are no dimensions provided. There's no materials. So we notice fairly early that one thing, it doesn't meet the roll bar requirements. So that was one thing that we were able to identify, that it doesn't have a continuous piece of metal as the roll bar. It's got a V shape with a weld in there. And other than that, it's got some structure. Because it didn't identify materials, we didn't know if the roll bar would meet our requirements, or the structure would meet our requirements, or if the crush zone would work. And it turns out in this car, the body was beautiful, was well done, but it was only 2 layers of carbon fiber. So there really was no material in there that gave it any structure to meet the crush zone. Whereas if we'd known that ahead of time, we probably could have identified that and saved them some frantic construction in the garage at the race. So this is another excellent drawing that we've received. And on this one, you'll notice I highlighted in red there the little block that gave the dimensions of the drawing, which is very helpful so we know what we're looking at. Another very useful thing is the bill of materials right here. It tells you what each part is and what they expected it to be used for. One additional thing that would have been really helpful to know actually what material each piece really was, as it didn't tell us, but overall, when looking at it, you can basically identify what the crush zones are, what the roll bar is. And while we don't know if the materials are, so we don't know if it's going to meet their criteria, the basic idea looks correct. We can see a single piece roll bar, we can see some crush zones identified, and we see basic structure. So missing some important pieces in the suspension, but overall, a very good drawing.
Jarrett, before you leave that drawing, I'd like to point out that if the driver is sort of back behind that roll bar, that would provide upper protection and meet our rules. But if you seat the driver in front of that, there's no protection from a side impact. So I would be very concerned about putting that driver on the track in the event that he would be struck from the side.
Yes, and this is again where having all the detail, having the driver in your model would be very helpful to help identify where we expected him to be. So, okay, and moving on to some electrical diagrams. The one on the left, you'll see, is a very simple diagram, but the things I like about it are it has color. We can clearly identify what the positive and negative wires are. We can find the fuse, we can find the controller. It's got the wires for the throttle, the wires for the motor. Some things I think could be improved on this one is, I haven't looked at the rest of their registration documents. I know that controller requires a 3-wire potentiometer for the throttle. So that's something that's going to be missing. We're also missing the switches. So those are very important components that are not shown in the diagram. The one on the right is a little bit fancier diagram. They didn't use color, which is fine, but they clearly labeled where their positive and negative wires are. And one of the things I really like is they included the line contactor. So if they're troubleshooting their not getting power to controller, they know they have something in there beside just the motor disconnect switches and the fuse. They know that they have an extra contactor in there that might be an issue or a place that they need to troubleshoot. One of the things that neither of these diagrams have is they don't show the interaction between the 12-volt and the high voltage system. Pretty much every controller out there needs some kind of enable switch, which is in most cases 12 volts, to turn on. So having those interactions to know what all the inputs to your systems are, and the same thing with your power trackers. Many of the power trackers require a signal in order to turn on. So having those interactions on your diagram and labeled is very helpful so that you know if a component is not working, you know what all the required inputs are. You know that it's not just power coming in from the solar array into your solar tracker, but you also need a switch for enable that either is providing 12 volts or might just be connecting 2 pins in the power tracker. So we very rarely see that on any of our electrical diagrams, but I think it's a very useful thing. And your electrical diagrams don't have to become huge messes. You can just put a little tab out that says, 2 12-volt system and show it on some other diagram.
Jarrett, the other thing that I would invite our participants to look at, it's like with these pictures in front of you, how much do you think the one on the left would actually help you troubleshoot a problem with the high voltage system? Even the one on the right that's got a lot more detail, when I go and take this and I stand next to a car where I've got power wires routed through and around things, in and out of the battery boxes, up to the ray and things like that, I have a pretty good conceptual note here. And for us, you tell us what you're actually doing with your car, which is helpful, but this isn't necessarily the best troubleshooting tool you could have versus actually taking and going a step further and maybe even labeling some of the wires, or like Jared keeps talking about, doing some color coding to match, or adding a note that tells you what color that wire is, or something so that when I very quickly need to troubleshoot and assess a problem, not only do I have something that conceptually tells me this is how things are connected, so this is where I want to go look. For example, I'll pick on a turn signal system or something. Neither of these have that. These are the wires I want to go look at because my brake lights aren't working. And this is where they run. That information isn't in here. And having been on both sides of this, I can tell you that that can be a lifesaver when you're in the middle of a race day, your brake lights stop working or something like that, or turn signals, so we pull you off the track. And having a good diagram that actually can be your roadmap to track down the wires so that you can quickly assess the problem can make the difference between it taking 20 minutes to fix or taking 4 hours to fix. And there you've shot your whole race session. So I just wanted to kind of add that in there, that think about that when you're doing these schematics. Yes, it's so that you can show us what you're doing and we can kind of help provide some feedback saying, this is something you might want to look at, or yes, this, the way it's drawn looks like it's compliant with the rules, but take it a step further and make it useful to you, because it's not that much more time invested in your drawing or your schematic, but it will save you time if you have to troubleshoot. That was all I wanted to say.
Yeah, and you're extending that on to the diagrams. When you're talking about putting things like fuses, actually having the fuse blocks in the right order so that you know the third fuse from the bottom is your turn signals and the top fuse is the horn is very, very helpful when you're trying to do things quickly, if you're trying to identify fuses and such things. And I have mentioned color. I tend to favor color for wires. And if you look at if you could go take apart your car, you'll notice that the wiring harness is full of different colored wires for this very reason. But there are an infinite number of ways to mark wires, from very expensive systems that will actually print the name of the wire on it to very cheap labelings where you just have numbers, or even a painter's tape with a Sharpie is good for identifying markers multiple places. Oh, sorry, someone was chatting. I was receiving questions. But having those identified in your drawing so you can identify your parts are very important. And with that, if anyone has any questions, I have reached the end of my presentation. Dr. Marks, Chris or William, do you have anything to add?
We have some friends from Siemens who are going to talk to us about their Solid Edge software designed to help you make good mechanical drawings and schematics. So I'd like to introduce our friends, Mike and Mohammed, and Matt Bruce are here. We'll turn the program over to you.
Hello, everyone. This is Mike Ashbaugh from Siemens. So to begin, I'm going to hand this to my colleague, Mohammed.
Thanks, Mike. Hello, everyone. I'm Mohammed Sajjad. And if you're a returning student, you probably saw me from last year's presentation. No, I'm not a Solid Edge rock star. That was just my colleague messing with me. But I am an application engineer, part of the Siemens Solid Edge academic team. I'm responsible for Solid Edge support and curriculum development for the academic institutions. My colleague who will be presenting with me today, Mike Ashbaugh, is a business development manager for Solid Edge Electrical Design. A little bit about him. Mike joined Siemens Mainstream Engineering in 2019 to support the Solid Edge portfolio products. He came to Siemens from Mentor Graphics as a senior application engineer and process consultant for the worldwide distribution sales channel. He holds a bachelor's degree in electrical engineering from Penn State and a bachelor's degree in physics from Westchester University. His focus is enabling Siemens customers to address the ever-increasing design complexities of electrical system in their smart connected electromechanical products. Mike, if you would go to the next slide. So when you think about CAD, what comes to mind? Just mechanical CAD, right? Designing something on a computer. Well, that was true in the past, but it has evolved into so much more. The Solid Edge portfolio, it's a portfolio of affordable, easy to use software solutions that allow customers, whether it's customers in the commercial market or customers like you who are competing in this competition of all sizes, to create virtual representations for every aspect, in their product development process. We have key solutions in mechanical, electrical design, simulation, manufacturing, technical publication, data management, and lastly, the collaboration, because we know collaboration across the team is very important. Solid Edge portfolio, it also enables digital transformation for companies of all sizes and shapes, from helping speed time to market and lead in their respective markets in an ever-changing environment. So, for today's discussion, we're going to focus on the electrical design pillar to discuss the intelligent schematics. So now I will hand it off to Mike to discuss more about the Solid Edge electrical wiring and harness design. Mike?
Okay, thank you, Mohammed, and thank you everyone for inviting me to join this. I turned my video on so you can see me. Maybe we make a better connection there with that. The electrical products here, I'm going to focus on Solid Edge wiring and harness design. That is a technology that Siemens acquired from Mentor Graphics, and very sophisticated software used to design automobiles and airplanes. And Siemens has taken that software module and made it available now to the smaller mid-sized business. So it's really powerful, industry-leading software, and that's one of the softwares that I support. And it was really nice to hear Jared and Chris talk before us. You'll see that the stories align quite well, so I was really happy with the message that they provided. So this software, to help us with electrical systems, we think of these smart connected products. So I just wanted to give you a visual. What's a good fit for software like this? Well, notice the car in the lower left-hand corner, right? You see the wires, you see they're bundled together as harnesses. That's the electrical nervous system to tie together all those sensors and monitors and some of the devices that Chris and Jarrett talked about, right? That has to work, right? Otherwise our product won't perform. But there's a lot of products today that have this type of need to connect these devices and sensors. In the middle, you see a device that's used in the hospital. Inside there's wires and harnesses. To the right of that, you see a snowblower, which is an electrical snowblower, lots of electronics in it. And today they make lawnmowers that are autonomous. Think of the electronics that goes in there, the wires, the harness, the sensors, and it has to work. And the industry today is really demanding more and more electronics. So I want to just set that stage for you and think about that, the electronics, right? The demand for these smart connected products, right, is really tremendous. And there was a recent survey that asked these engineering teams, right, electrical and mechanical engineering teams, what is the value that's added by the electronics and electrical systems in these next generation products that you're creating? And the survey said that the value from the electronics in that system, right, 70% said that value was increasing after each product. And 37% of those said that value was increasing significantly. See, what companies have realized, this is how they differentiate their products and they stay competitive, by adding those electronics, the features, the functions. The thing about that, though, it doesn't come free. There's a cost associated with that when it comes to the design complexity. And Jarrett and Chris talked a lot about the communication. There's a lot of issues associated with that. So I just show you here on the right-hand side, right, what do the companies say about this design complexity? I'll just look at a couple of these, right? It does delay the time to market. 40% of them said that. There can be lost revenue, project overruns, design inefficiencies. You know, all that communication that Jarrett was sharing with us, not just within the team, but what about the third-party people that you use to build these subcontractors to do the harnesses and things like that? Or poor product quality. Maybe it works, but the margins of failure really isn't where you really liked it to be. These are really tremendous pressures that the design engineers, they do feel this. But I wanted to bring another thing too, not just to get the product to work. Designs get more complex, especially with electrical work when it comes to compliances. So here, depending on the industry you're in, there's standards or rules or requirements for that industry. Or if you're going to work in certain parts of the country or different regions, there's policies and regulations associated with that. So here's the thing. You have to follow all those compliances, and at the same time, you have to be transparent. And what that means is you have to show that you followed those compliances. So all this documentation that Jarrett and Chris talked about, the importance of doing that, our design content needs to be readable. We have to be able to share the information, not just for debugging for our own needs, right? But to share it to show that, yes, we can sell this product or deliver it in your country or your region. So what does this mean here? This is the reason I wanted to start with this, is that the engineering teams and companies recognize those older methods, those traditional methods, they just no longer work today. That's really the message. And it all comes back to this too, right? We got cost deadlines that we're targeting to stay competitive. Time is always important. And the risk, are what we're doing, the engineering decisions we're making now, are they the right ones? How do you validate that? And all of these things come into play, but depending on what your product is, where you're trying to sell it, what your competition is, some of these will have unique priorities over the other. So excellent messaging that Jarrett and Chris shared with us. Here's an example here, like what happens if we get this wrong, right? Here's an example that over 1 million trucks had to be recalled by Fiat Chrysler because there was a short in one of the airbags due to some rubbing that was going on, and the airbags would unexpectedly go off. So not only did they have to replace all those airbags and get that recalled, think of the branding issues and challenges and costs associated with that. These are real concerns from all levels when you're putting these products together. Sounds real simple. Maybe it's a little harness, right? But look at the cause if you get it wrong. That's why people invest in this and want to get it right. And Jarrett, I kind of had to smile when you said CAD software is expensive. And that's true, right? When you talk to people, they say, my goodness, this is expensive. But that's all relative too, right? Depending on where you find the problem, that could really be expensive. And that's why people invest in improving their process. Make sure you have the right software with that. So I show this electrical schematic here, and think about what Jarrett and Chris shared with us. This is what we would call a non-intelligent schematic, right? We could essentially have drawn that in a whiteboard in our conference room. To me, I look at this, it's some lines, it's some circles, it's some boxes. And we essentially really don't know what's going on here unless it's visually captured. Just like Jarrett said, everything in here is black. We don't have any colors, right? So if it's not labeled on here, we don't know what it is. And we certainly don't know the characteristics of the elements on this particular schematic. And believe it or not, some companies still use this type of approach. Not as many, because it just doesn't work with complicated designs. So think about, if you want to generate the bill of materials from here, make sure you got all the components. You know, Chris talked about that. People miss components from their schematic. Well, here, this is a good way to make a mistake like that, because you have to manually list all the elements in your design. And it's easy to make those human mistakes. So I'm going to try to, emphasize that message that they were talking about in the previous presentation. Look at this example here. This is an electrical schematic, but it has intelligence in it. This is actually designed and captured in a solid edge wiring design, which I'm going to show you a little demonstration of that. So it's a nice clean schematic. We have an element down here where you see my cursor. This is a switch, right? And notice how clean this schematic looks. However, we have so much detail associated with one element. The light switch in the middle, I can highlight that. I know what manufacturer it's from, what the part number it is, the performance of the voltage and current. There can be a data sheet link tied to it, right? Because we're gathering information, building our schematics from a centralized electrical parts library. That's what we want to do, so we build intelligence into our schematic. So if we generate a bill of material from here, the data automatically comes from the schematic into tables, nicely formatted how our engineering team wants to see it. We can have another format that's targeted for people that will order the parts. Again, I'm talking to engineering teams kind of on the commercial level, but you can see the value of that. It's going to remove the human error, and think how quickly and efficiently we can work here, right? And that's where it saves time, saves cost, and we're in a very competitive market, right? We want to offer that best product. I'm going to show you some other things in the demo, but the blue lines are actually wires. A wire, as Jared said, right, it has a color, has a part number, it has a diameter, it has a material. Notice we don't have to view all that looking at this schematic the way it is here. Now, a schematic can have multiple sheets. You can have 300 sheets. However, it's easy to find the information because these software systems have design browsers. So you can select and filter through information and find out what page it is. In the demo, you will see when I select on the wire name on the far left, that's going to jump and take us to the page where we will find where that signal goes. So just as we talked about, the user can debug this information with this intelligence. Now let me say one more thing before I move to the next slide. You know this diagram came from solid edge wiring design because I told you it's a very advanced electrical schematic tool. However, we could have drawn that in Visio or PowerPoint or something else, and it wouldn't have the intelligence underneath and behind it. So just because it looks like this doesn't mean that it has the associated data, right? With PowerPoint, it would still just be lines and circles and boxes, right? But we use an intelligent electrical schematic, we get the details that we need. Okay, I'm going to talk a little bit about the traditional approach, right? Electrical and mechanical engineers working together. And just, again, think about what Jared and Chris shared with us, the ability to communicate, right? So here on the right-hand side, we have a young lady. She's our electrical engineer, and she's capturing her schematic. On the left-hand side, that will be our mechanical engineer. Now notice the big line in the middle, and it's depicting that these two individuals are working in isolated environments, different offices. They're definitely using different software. They could be in different buildings or different states. And what happens here is because they're using like this manual entry, their ability to share information is very tedious. The young lady would have to call the gentleman on the phone and say, here's what I'm doing, or they'll send a Word document, very manual in nature. The other thing with that, it's not efficient, so they don't do that very frequently. And what happens there? They're both proceeding with their design, not collaborating because it's too challenging. They get towards the end of the design cycle and phase, then they start communicating and they realize we have some problems. We have some issues, right? Jared talked about issues you find out late. Now what do? You're running out of time. Trying to fix something later is much more expensive. So if you got to get this product out the door, right, what decision do you make when it comes to cost and time and, right the first time kind of a thing? So oftentimes your options are very limited, right? And we want to change that. So Siemens, right, develops software to help these electrical and mechanical engineering teams to bring those two environments together. And that's what the solid edge wiring and harness design software is that I'm going to share with you. Okay, this is the name of the product, solid edge wiring and harness design. So under our academic program, which Mohammed will talk at the very end of our presentation, you would get access to this. So I'm going to go through the wiring design, what that does for you, and the harness design. And then I have about 5 minutes of a video to show you, show the software for you. Okay, so the wiring design, this is where you capture your schematic. Just like Jared said, right, you can produce your schematic. The difference there is when you put a device or a component onto the schematic, you're pulling from an electrical parts library that's provided by the software. Now, the reason that's important, right, anyone working on the design is pulling from the same library. That way we know the data is complete, we know it's accurate. That's how companies make sure they're using the right elements, because they protect the information that's in that centralized library. That's how they do that. And when we place the component onto the schematic, now you can run it, connect it together with wires. This consistency with styling. Again, going back to what Jared said, styling. That's how the engineering teams can control the look and feel of a drawing. We use the same title block. We use the same font sizes. We use the same labeling mechanism. Why do we do that? Exactly as Jared said, because somebody else may have to go read your diagram, and you want to have the ability to be consistent in what this means. Remember, they talked about the person that did the electrical wiring didn't show up on race day. Right? That created a problem. Well, if we have consistency in our drawings along the company style, company standards, people know how to read and convey the information. So it's a tremendous asset when you're really working with those tight schedules. Design rule checks. What do I mean by that? That means as you're running wires, connecting these devices together, you cannot use the same wire name, for example, more than once. So if I type that in, the tool is going to tell me you can't do that. Color codes it in red, flags that as a problem. That's just one of many checks. So what's that doing is it's making sure that we're correct as we go, and we don't wait till later on down the design stream there and find out, ooh, something was wrong. Right? We already have enough challenges as it is, because remember, our competition down the street, right? They have smart engineers too, right? And they're working to have more electronics, better functionality at a lower cost, and meet the market window, right? It's very competitive. And then finally, simulation. This is what's really neat. I'll show you this in the demonstration. That circuit that we looked at, we can actually simulate and make sure that it functions properly. Jared talked about some switches that were missing, right? We would be able to determine that, hey, we're missing some switches in here, or the switches we have are in the wrong position. We can actually do functional simulation in this product here called Solid Edge Wiring Design. Okay, let me move on to the harness design, right? This is the same software, right? But we'd still give it these two different names. In the harness design, we read the wiring diagram information. And again, Jared and Chris talked at the beginning, right? Always have a wiring design. Well, even though we're doing a harness, we want to read that information from our wiring design. In harness design, here's where we do the layout. It is also connected to the electrical parts library. So what that means is, excuse me, what that means is as we're picking out a connector, it's going to make sure that the wire sizes that get crimped in the connector are the right size. All that information resides in the electrical parts library. So we get automation associated with that. And then finally, harness documentation. both of these products automatically generate the documentation. That's exactly how you're going to reduce the risk of missing a part, right? Not making sure that the bill of material is complete. If you change something on the drawing, it updates the documentation. We don't have to worry about that being in sync. Now remember, not everybody does this. There are still people today that don't use some of these more advanced tools. If they're in an industry that is not as competitive, right, they can get away with doing it. But the more competitive this gets, the more need for that. Okay, I'm just going to take a moment here and talk a little bit about the data flow. You know what wiring design is, you know what harness design is. I'll make this kind of brief, but I just want to give you a nice visual of where the data is being captured and how we're moving it around. So in wiring design, that's where you capture your schematic. And we're pulling those parts from an electrical parts library. We give you a started library, but your team will also want to add their own parts. That's very common. It's part of a good engineering flow. Once you have the wiring design done, that information is shared with harness design. And in harness design, that's where you add your grommets, your clips, your connectors, insulation, whatever it is, and determine what the length of this harness needs to be. Now we could stop right there, and that's the electrical team. They're the ones doing that work. However, we get better collaboration if we can connect this environment with our Solid Edge MCAD team. And that's where Solid Edge comes in. So the word I'd like you to remember through this conversation here is connected mode. And just look at that arrow. It's depicting that we can share information, the wire information, to the Solid Edge MCAD environment. That's really critical. That's a push button operation. So compare this to the traditional method that we described where a young lady and man doing the mechanical in that separated environment. They don't have a chance. Here with an environment like this, with these Siemens tools, push button, we can share the information. So what's going to happen here? Because it's so easy to share it, I can send over the wire information anytime the MCAD team is ready for it. They can accept it, they can do their routing, and then they send me back the information saying, here's the new wire lengths. And what are we doing? We're collaborating. We're finding out if there's any issues early, because that saves us time and money and it reduces the risk. So that's the important collaboration. Okay, I have a couple slides here before I get to the demo. And what I want to do with these couple slides is just emphasize the importance when we're approaching these designs. One of the key things that we try to do is optimize the design. We're talking about these solar cars, right? You're optimizing to win, to be faster, to save energy. Well, same with mechanical and electrical teams here. So the mechanical team, because we can collaborate, right? They want to know, look, if I run the wires this way, will it be rubbing on parts of the assembly that will be moving? Much like that truck with the failed airbags. That's what keeps the mechanical engineers up at night. They're running wires and maybe it's going through a hostile environment, a part of the assembly, whatever this thing is that they're building. Maybe there's an area in there that gets a little bit too hot, right? And because of that, maybe the performance of the wires will be different in such a way it'll affect the electrical piece of it. They have to be concerned about that. What if they don't have enough room for the harness? You do all this work, bundle the wires together to find out, look, it's not going to fit through this arm or whatever it has to be. We want to find that out early so we can make some changes, get back to the electrical team and said, look, here's what we ran into. We're going to try to do this. It's going to extend the length of the wires. Will that be okay? We're collaborating. We'll say, what if we do this? What if we do that? That's how we design optimized products and do a good job and stay competitive with that. Let's look at the side of the electrical engineer. This is where I've kind of spent most of my career doing simulations and stuff like that. Here's a schematic and they're actually running a simulation. I'm going to show that to you in the demonstration. The color of the wires, because it's green, it means there's current flowing through it because we're running simulation. But what are the electrical engineers concerned about? Do the signal wires have enough strength when it finally signal gets to the receiving components? That's what they want to know. Am I sizing the wire diagrams properly, right? We don't want the wires too thick, right? Because then we're over designing it. That could be increased in cost. It hurts us with the room for the harness, right? Again, it depends on the product. Are these critical or not so critical? It really depends on the product and what our design goals are. What are the requirements? Are the fuses a proper size? Are they in the right place, right? Jarrett talked about that, a couple of different examples, right? So this is what the electrical engineering team is concerned about and asking. Okay, so if we compare this now, right, because we can automate with this software from Siemens, that's going to give us the ability to keep those costs lower. Because we can collaborate, we can shorten the cycles, we can communicate, we can find those issues earlier, and then verify. We can check along the way through simulation. Using the centralized library is going to help us build a valid schematic and avoid those costly errors. Okay, this is the first of the demos. It takes about 4 minutes to go through here. I might pause a little bit along the way. So this is a schematic in solid edge wiring design. I'm going to just let this play, and you're going to see the individual can toggle switches here in the switch here and see the performance of it. So let me just let this run. What you're seeing, the simulator is running, and because the wire is cyan or light blue, it means there's no current flowing through that. So again, going back to what Jarrett said, you toggle switches to see if you're getting the performance. Could be missing a switch for that matter. So and what this individual will find is that, hey, we're not getting power coming to the schematic. We're going to need to go debug that. So here he's going to click on this wire name here. It's going to take him to the schematic sheet that has that. There we go. And then we can see the schematic. You can see the green wires coming in, and this ignition switch in the middle is in the wrong place. He's going to toggle that. You can do this live functional simulation right within the schematic. That's the advantage of having intelligent schematics with a simulator here. I'll let him flip this switch here to position 2, and you'll see the wires turn green. And hopefully in your monitor, you can see that now he has green wires and the current's going through that. Okay, I'm going to just move forward and stop the demos there. Okay, and Mohammed, I'm not even going to do the summary. This was my last summary page, right? And we will make these presentations available. And with that, Mohammed, we have 1 minute, and I'll let you talk to this slide and we'll wrap up.
Okay, thank you, Mike. So what's in it for you as competitors in the solar car challenge? You know, as competitors, Siemens is making the entire solid edge portfolio available for you to use at no cost. You know, the bundle includes 8 of the most popular tools used in the industry today. That includes MCAD, ECAD, simulation tools. So you're not bound to the entire portfolio. You can pick and choose, you know, which software you would like to use and leave out. Anything that you don't want, you can leave out. So these tools are only available by way of our academic grant from Siemens. You know, for consideration, someone like a teacher or authority figure associated with your school, could be a teacher, parent, or you know, educator. They can submit an online grant. There's no deadline. A grant can be submitted at any time and usually takes a few days to complete. So, you know, feel free to email one of us for the links to the grant. It awards a subscription that's good for 3 years, after which the team can simply reapply should they wish to continue using the software. So, you know, and you get up and running faster, you have free access to the complete library of curriculum, you know, training and other resources, as well as solid edge certification exam, you know, which can be, you can take and study for, which can be taken for free. An industry recognized certificate of completion which can also be provided after the completion of the exam as well. So that's the entire presentation. Thank you for listening to us. And if you have any questions, feel free to reach out to us. I'm sure Dr. Mars can provide you all our email, so don't hesitate to reach out to us. Thank you.
Mohammed, it's good to hear you again. We enjoyed your presentation last year. Thank you for being a part of it. Alex, thank you for everything that you've shared with us. And we want you to know how much we enjoy our support from Siemens. You have done a great job helping us in the past. This past year, you were the sponsor of our awards to the oral presentation videos that we presented, helping to motivate all of our teams. So thank you again. Thanks to everyone for tuning in for today's webinar. We look forward to seeing you in 2 weeks. Have a good day.